Deep inside forgotten NASA archives lie the blueprints for our cosmic future. These are not just old plans, they are revolutionary engines and Starship concepts shelved for decades, ideas powerful enough to reach Mars in mere weeks. Unlocking these lost designs today gives us the keys to solving the biggest problems in space travel. You will discover propulsion systems that harness the power of the sun and learn how we might one day build permanent cities in orbit. What stopped these incredible machines from being built, and could they be the very things that finally take us to the stars? The sheer audacity of Project Orion is almost incomprehensible today. Think of a ship not burning fuel, but riding a continuous storm of nuclear fire. Envision a spacecraft so vast it could house an entire community, its journey powered by setting off atomic bombs, one after another, behind a colossal metal shield. Each explosion would slam into this pusher plate, transferring immense momentum through a system of giant shock absorbers to hurl the vessel forward. This was not science fiction. It was a seriously researched design, backed by some of the brightest minds of the era, promising to open the entire solar system for exploration. With this method, a voyage to the rings of Saturn could take less than a decade, a journey we currently measure in lifetimes. The physics was sound, the engineering plans were detailed, and the potential was staggering. So why do we not have nuclear pulse starships today? The dream of Orion did not collapse under the weight of its own ambition. It was ultimately grounded by the very real-world fear of radioactive fallout and the political firestorm of the Nuclear Test Ban Treaty. The technology that could have given us the stars became a casualty of the Cold War, a powerful reminder that our greatest obstacles to space are often not found in the void, but right here on Earth. While Orion promised to ride a storm of fire, another forgotten project sought to refine that raw power into a controlled, steady burn. Deep in the Nevada desert, engineers built and tested a completely different kind of nuclear engine. Picture a rocket nozzle glowing with a clean, blue-white flame, a torrent of superheated gas blasting out with silent, immense force. This was not chemical combustion. This was the NERVA engine, where liquid hydrogen was pumped through the white-hot core of a compact nuclear fission reactor. The hydrogen, heated to temperatures far beyond what any chemical engine could withstand, expanded violently and shot out the nozzle, creating thrust with more than double the efficiency of the best conventional rockets. It was a simple, profound principle: turn a reactor into the most powerful furnace imaginable, using its heat to accelerate propellant. The NERVA program was not just a paper concept. It was a roaring success on the test stand, with engines firing for long durations and proving they had the power and reliability for a realistic manned mission to Mars. These were not bombs going off, but a smooth, controllable, and incredibly potent source of propulsion. So why did this proven technology, this bridge to the Red Planet, end up in a museum instead of on a launch pad? The answer lies in a shift of vision. With the Apollo program concluding, the political will and funding for ambitious deep space missions evaporated. The NERVA engine was a casualty of a new era that looked away from the stars and back toward Earth. Yet the ghost of NERVA never truly left the room. Its foundational principles are now being resurrected, pushing engineers to ask the next logical question. If we can tame the power of splitting atoms for thrust, what becomes possible when we learn to fuse them together? The leap from fission to fusion was a dream of pure, star-like power, and in the 1970s, a team of British engineers dared to draft that dream into a full set of blueprints. Their creation was Project Daedalus, an unmanned interstellar probe designed for a one-way mission to another star. This was not a vague concept but a detailed engineering study for a vessel that would use nuclear fusion, the very process that lights the sun, as its engine. The system was both brilliant and complex. It would fire tiny pellets of fuel, a mix of deuterium and helium-3, into a reaction chamber. There, powerful electron beams would strike each pellet, compressing and heating it to the point of fusion ignition. Imagine a continuous, controlled starfire, a rapid sequence of miniature suns blooming in that chamber. Each micro-explosion would generate a tremendous pulse of plasma, channeled out by a magnetic nozzle to push the ship forward. This engine would not shut down after a few minutes. It was designed to fire continuously for nearly 4 years, building up speed until the Daedalus probe was traveling at an almost unimaginable 12% of the speed of light. At that velocity, a journey to a nearby star like Barnard's star could be completed within a single human lifetime. But such an ambitious design came with one monumental obstacle: fuel. The chosen propellant, helium-3, is incredibly rare on our planet. The Daedalus solution was as audacious as the ship itself. It proposed mining this precious fuel from the atmosphere of Jupiter, using massive automated harvesters floating in the gas giant's clouds. This single requirement highlighted a profound truth about our future in space. Truly revolutionary travel demands more than just a faster engine. It requires an entire industrial ecosystem beyond our world. Daedalus remains the most comprehensive blueprint for an interstellar vehicle ever conceived, and its legacy is alive today, inspiring modern initiatives like Breakthrough Starship. It proved that reaching for the stars is an engineering problem we can begin to solve. Yet, this grand vision of fueling starships at Jupiter forces us to confront a practical question. Where would we build such a vessel in the first place, and how would we supply its epic journey? Building a starship at Jupiter is an epic undertaking, but every great journey needs a home port. Long before we could construct such a vessel, we would need a way to assemble and service it in the void. This brings us to one of NASA's most practical yet overlooked concepts, the Space Tug. Envision a versatile, reusable spacecraft designed never to touch a planet's surface. Its entire existence would be in the weightless realm between worlds, a true workhorse of the high frontier. The Tug was conceived as a multi-purpose orbital vehicle, a single system that could be configured for a wide array of critical jobs. It could use efficient chemical rockets for quick, powerful maneuvers or switch to slow, steady electric thrusters for long-duration, fuel-efficient hauls. One day it might function as a cosmic tow truck, rendezvousing with a stranded communications satellite to refuel it or boost it back to its proper orbit. The next, it could transform into a construction crane, carefully maneuvering large modules into place to assemble a space station or an interplanetary shipyard. Its core innovation was reusability. Instead of building a new, expensive spacecraft for every single orbital task, the same reliable tug would be refueled and repurposed, drastically lowering the cost of operating in space. It was the key to building a sustainable infrastructure in Earth orbit, a logistics network that would make everything else possible. So what happened to this orbital Swiss Army knife? Like so many grand ideas from that era, it fell victim to budget realities. With finite funds and political attention shifting to the Space Shuttle program, the pragmatic tug was deemed unnecessary. Its functions were folded into the shuttle's intended capabilities, a compromise that never fully materialized as envisioned. Today, as private companies plan new space stations and NASA looks toward a permanent lunar gateway, the need for a dedicated, reusable orbital transfer vehicle is more apparent than ever. We are recognizing that to live and work in space, we need the equivalent of a pickup truck, not just a sports car, but constructing these orbital hubs presents its own profound challenge. Once we have built our stations and shipyards in the void, how do we protect the people living inside them from the constant, invisible rain of cosmic radiation? An invisible fortress surrounds the ship, a protective bubble born not from thick walls of metal, but from pure magnetic force. This was the promise of active magnetic shielding, a NAS, a concept designed to conquer the silent, invisible killer of deep space, cosmic radiation. Our planet is cocooned by its own natural magnetic field, the magnetosphere, which deflects a constant hail of high-energy particles from the Sun and distant galaxies. For astronauts venturing beyond this protective embrace, these particles pose a severe threat, damaging human cells and increasing the risk of cancer over long missions. The traditional solution is passive shielding, piling on dense materials like lead or storing water tanks around the crew cabin. But the weight of this armor becomes astronomical for a ship destined for Mars or beyond, making the entire mission impractical. The magnetic shield offered an elegant alternative. The idea was to deploy large, superconducting coils around the spacecraft, creating an artificial magnetosphere. As deadly charged particles approached, this powerful magnetic field would gently bend their trajectories, guiding them safely around the vessel like a river flowing around a rock. The crew inside would live and work in a safe zone, protected by an energy field they could not see or feel. While the concept required substantial electrical power to sustain the magnetic field, it would ultimately be far lighter than hauling tons of physical shielding across the solar system. With modern advances in high-temperature superconductors and compact nuclear reactors, this once futuristic idea is edging closer to reality. It transforms the problem from one of brute mass to one of finesse and power management. Yet, creating this protective magnetic bubble demands a tremendous and reliable source of electricity, a challenge that points directly to another revolutionary concept waiting in the archives. Sunlight itself can become a gentle, endless wind for a starship. This is the promise of the solar sail, a concept that trades roaring engines and volatile fuel for vast, silent wings. Picture a spacecraft equipped with sails not of canvas, but of a mirrored film thinner than a human hair, stretching for kilometers across the emptiness. These sails do not catch air, for there is none in space. Instead, they are pushed by the physical force of light. Every photon from the sun, though it has no mass, carries a tiny amount of momentum, and when it reflects off this gigantic mirror, it gives the sail a minute continuous push. There is no explosion, only a constant, accumulating pressure. Over weeks and months, this gentle shove builds into significant speed, allowing a vessel to cruise across the inner solar system without ever needing to refuel. It is the ultimate example of efficiency, a propulsion system that runs on starlight. NASA proved this was not just theory with its nanosail D mission, and Japan's space agency successfully flew its own solar sail, Icaros, demonstrating controlled flight using only sunlight. But the true potential lies in more ambitious designs like the solar moth, conceived for dedicated interplanetary travel. The challenge has always been one of scale and delicacy. To generate meaningful thrust, these sails must be enormous, yet to be launched from Earth, they must be packed into a tiny volume and then unfurled perfectly in the harsh environment of space. For decades, the material science to achieve this reliably simply did not exist. Today, that is changing. The development of ultra-strong, lightweight wonders like graphene is turning this forgotten concept into a tangible future technology. We are learning that the simplest ideas, harnessing the free and abundant energy of the sun, often demand the most sophisticated engineering to bring to life. Yet, as effective as sunlight is close to home, its push grows fainter the farther a ship travels from the sun, its gentle wind fading to a whisper in the outer dark. To voyage truly far, we need a source of power that does not diminish, a way to bring our own star with us. That same solar power that pushes a sail could be captured on an unimaginable scale, not for propulsion, but to energize our entire world. In the 1970s, amid oil shortages and growing energy fears, scientists from NASA and the Department of Energy drafted plans for a solution that looked like pure science fiction. They envisioned not single satellites, but vast constellations of them, each one a power station parked in a high geostationary orbit. From that fixed perch, a satellite would bask in perpetual, unfiltered sunlight, completely free of clouds, night, or atmospheric interference. Its surface, stretching for kilometers, would be a sea of photovoltaic cells gathering this raw solar energy. But how do you get that power all the way down to Earth? The answer was as elegant as it was revolutionary. The satellites would convert the collected electricity into low-intensity microwaves, beaming this energy wirelessly down to massive receiving antennas on the ground, called rectennas. These fields of metal mesh would safely absorb the microwave beams and convert them back into usable electricity, feeding a clean, limitless power supply directly into the grid, capable of energizing entire cities day and night, regardless of the weather below. The vision was a global energy network fundamentally decoupled from the burning of fossil fuels. So why did this breathtakingly ambitious plan fail to launch? The sheer scale was the primary obstacle. The cost of launching the thousands of tons of material required to build these colossal structures was at the time utterly prohibitive. The technical hurdles of precise wireless power transmission over such vast distances also seemed daunting. The project was shelved, another grand concept waiting for its time. But its time may be now. With the dramatic plunge in launch costs driven by reusable rockets and the rapid development of robotics for automated assembly in orbit, the economic logic that once killed the idea is being inverted. We are on the cusp of being able to build such immense structures without bankrupting nations, and this changes everything, not just for Earth's energy, but for the future of space travel itself. A permanent, high-power infrastructure in orbit provides the one thing the most advanced propulsion systems always crave, an almost limitless supply of electricity. With that kind of power available, we can finally begin to experiment with engines that were once thought too energy-hungry to ever be practical. Containing a miniature star within magnetic fields was the radical premise of the gas-core nuclear rocket. This concept took the principles of NERVA and pushed them to a breathtaking extreme. Instead of a solid reactor core, this engine would create a swirling, superheated cloud of uranium gas, a tiny artificial sun held in place by powerful magnetic containment. Within this contained inferno, nuclear fission would rage at temperatures far exceeding the surface of our own sun. The propellant, typically liquid hydrogen, would be injected directly into this raging plasma cloud, instantly heated to an unimaginable degree, and then expelled out the nozzle at velocities that dwarf even the most advanced engines we have today. The potential was staggering. Such an engine could achieve a specific impulse, the measure of rocket efficiency, many times greater than anything chemical or solid core nuclear. A journey to Mars could be slashed from many months down to a matter of mere weeks, but this immense power came with an equally immense engineering nightmare. How do you bottle a miniature sun without the bottle melting? The fundamental challenge was perfect magnetic containment. If that superheated, radioactive plasma cloud so much as brushed against the physical walls of the combustion chamber, it would instantly vaporize them. The entire system had to be a perfect balance of forces, a magnetic cage for a nuclear firestorm. While the physics was understood, the materials and control systems of the era were simply not up to the task. The gas core rocket thus remains one of the great what-ifs of astronautics, a concept so powerful it still defines the upper limit of what we believe is possible with fission-based propulsion. It is a humbling reminder that our ambitions can easily outpace our technology. Yet, even if we could build an engine capable of such blistering speeds, how would a ship navigate with the required precision across such vast and empty distances? This need for celestial accuracy brings us to a surprisingly ancient yet supremely reliable guidance system, one that requires no ground control and never loses its signal. A ship lost in the endless ocean of space could find its way home by reading the cosmic clockwork of the dead. Deep within NASA archives lies a navigation system that does exactly that, a method for finding your position by listening to the heartbeat of the universe. This is the X-ray Pulsar Navigation System, or XNAV. It transforms certain spinning neutron stars, the lighthouses of the galaxy, into a celestial GPS network. When a massive star dies in a supernova, its core can collapse into a city-sized sphere of unimaginably dense matter, spinning hundreds of times per second and beaming out powerful radiation from its magnetic poles. From our distant vantage point, these beams appear as perfectly regular pulses, like a metronome ticking with atomic clock precision across thousands of light years. Each pulsar has its own unique rhythm, a signature pulse rate that distinguishes it from all others. The principle of XNAV is elegant triangulation. A spacecraft equipped with a sensitive X-ray telescope would lock onto the signals from 3 or 4 known pulsars. By meticulously measuring the minuscule differences in the arrival time of their pulses, the onboard computer could calculate the ship's exact location in 3-dimensional space, relative to those fixed celestial landmarks. The accuracy is staggering, potentially pinpointing a vessel's position within a few kilometers anywhere in the solar system, and even into interstellar space. This autonomy is its greatest power. It severs the tether to Earth. A mission to the outer planets or a voyage to another star would no longer need to wait for a slow radio signal from a ground-based antenna to tell it where it is. The ship would know for itself in real time, capable of making course corrections instantly. The components for this system, once the stuff of pure theory, are now within our grasp. Modern X-ray detectors like the ones on space telescopes have achieved the required sensitivity, and our atomic clocks have grown smaller and more precise. We are building the very tools needed to read the map written in starlight. Achieving this level of self-reliant navigation is not just an incremental improvement, it is the fundamental key that unlocks a far grander ambition. It is the essential prerequisite for building not just ships, but entire worlds on a scale that dwarfs anything humanity has ever attempted. 20 miles of Earth, recreated inside a hollow tube spinning silently in the void. This is the O'Neill cylinder, a space colony so vast its interior landscape includes rolling hills, flowing rivers, and towns under a long strip of brilliant blue sky. You would not feel like you were inside a machine. You would feel like you were standing in a wide, sun-drenched valley that stretches to the horizon in both directions. The secret to this earthly paradise is rotation. As the colossal cylinder turns, centrifugal force pins everything to the inner surface, creating a perfect 1G of artificial gravity. Vast alternating windows run the length of the cylinder, with giant mirrors outside that pivot to reflect sunlight inward, creating a natural cycle of day and night. This was not a fanciful artist's concept. It was a serious design by physicist Gerard K. O'Neill, backed by detailed NASA studies in the 1970s. These colonies were envisioned as permanent new frontiers, built at stable Lagrange points where the gravitational pulls of Earth and the Sun balance out. They promised more than just living space. They offered a solution to terrestrial problems like overpopulation and resource depletion, while providing a permanent home for the workers who would build the ships and factories of a true spacefaring civilization. The vision was breathtaking, but the practical hurdles were equally immense. Constructing a structure of that scale in orbit would require more metal and material than our entire global industry could provide at the time. The cost of launching it all from Earth was quite simply impossible. This single, monumental problem of sourcing raw materials forces a radical shift in our thinking. If we cannot possibly lift what we need from the bottom of Earth's gravity well, then the only logical solution is to find it somewhere else, somewhere without any gravity well at all. The Moon holds the raw ingredients for our future in space, and the most efficient way to ship them is not with rockets, but with a silent, electromagnetic slingshot. This was the lunar mass driver, a celestial cannon designed to fundamentally reshape our economy beyond Earth. Picture a long, track-like structure built on the lunar surface, powered by solar arrays that soak up the endless sunlight. Instead of explosive chemical propellants, it uses a series of powerful electromagnets to accelerate a magnetically levitated capsule. One by one, these capsules, filled with processed lunar soil or raw ore, would glide down this track faster and faster until they are flung off the end at a velocity just over 5,000 miles per hour. That is all it takes to escape the Moon's weak gravity and thin atmosphere, sending the payloads on a precise trajectory into space. There, automated tugs would intercept these free-flying parcels of material, towing them to construction yards in orbit. The energy efficiency is staggering. Launching the same mass from Earth would require thousands of times more fuel and cost, trapped as we are by our planet's deep gravity well and thick air. The mass driver transforms the Moon from a silent rock into the most productive quarry in the solar system. Its soil is rich with oxygen-locked-in minerals. Its rocks contain metals for building structures, and the water ice hiding in its polar craters can be split into hydrogen and oxygen, the very components of rocket fuel and the air we breathe. This single machine provides the foundation for everything else. With a steady, affordable stream of materials flowing from the Moon, we can begin constructing the O'Neill cylinders, fuel interstellar probes like Daedalus, and build the power satellites that will energize it all. It creates a self-sustaining cycle where we live in space using what we find in space. But this bounty of resources unlocks an even more profound possibility. What if we could design a ship that never needs to refuel at all, one that simply gathers its propellant as it flies through the void? The ultimate engine would need no fuel tanks at all, gathering its own propellant from the emptiness between the stars. This is the Bussard Ramjet, a concept where the ship itself becomes a cosmic fisherman, casting a net of magnetic fields light years wide. Proposed by physicist Robert Bussard in 1960, the design called for a colossal electromagnetic funnel, or ramscoop, stretching thousands of kilometers ahead of the vessel. As the ship plowed through the galaxy, this invisible net would sweep up the stray hydrogen atoms that drift through the interstellar void. These atoms would then be funneled into an onboard fusion reactor, compressed and heated until they fused together, releasing a torrent of energy to propel the ship forward. The elegance was breathtaking. By not carrying its fuel, the ship could avoid the tyranny of the rocket equation, accelerating continuously for years. In theory, this process could push a vessel to a significant fraction of the speed of light, making interstellar voyages within a human lifetime a real possibility. It was a perfect closed-loop system, a ship feeding on the thin soup of the galaxy itself, but later, more detailed analysis revealed a critical flaw. The very medium the ship needed to collect, the hydrogen in interstellar space, is so incredibly thin that it behaves more like a mist than an ocean. The magnetic scoop, in order to gather enough fuel to sustain fusion, would have to be unimaginably vast, and that immense structure, plowing through even that thin mist, would create a form of drag. The resistance of collecting the fuel might actually become greater than the thrust produced by burning it, at least within the relatively sparse regions of our galactic neighborhood. The Ramjet could find itself starving for fuel while simultaneously being slowed by the act of trying to collect it. Yet the core idea was so powerful it refused to die. It remains a cornerstone of interstellar thought, inspiring engineers to design clever variants that use more powerful lasers or different fuel mixtures to overcome the drag problem. But solving one puzzle often reveals another, even more profound challenge. To truly conquer the void, we might need to stop thinking about pushing against anything at all, and instead learn to pull the fabric of space itself. The ultimate shortcut through the universe would not involve moving at all, at least not in the conventional sense. A warp-drive spacecraft remains perfectly stationary inside a bubble of normal spacetime, while the fabric of the cosmos itself does the moving. The space in front of the vessel is massively compressed, pulling the destination closer, while the space behind it is dramatically expanded, pushing the point of origin farther away. The ship simply surfs this engineered wave in the continuum, theoretically achieving speeds that defy the cosmic speed limit of light. This is not science fantasy, but a rigorous, if speculative, mathematical solution to Einstein's equations of general relativity, first formulated by physicist Miguel Alcubierre in 1994. Inside this warp bubble, the crew would experience no acceleration forces, no time dilation, and would be completely protected from the crushing tidal forces that would exist just outside their safe pocket of reality. The journey to a star 4 light-years away could feel like a brief afternoon cruise. The concept is breathtaking, but it comes with one monumental, seemingly insurmountable problem: the energy bill. The original calculations suggested that creating and sustaining this warp bubble would require an amount of negative energy equivalent to the mass of the entire planet Jupiter. For decades, this single requirement placed the idea firmly in the realm of thought experiments. Yet the story did not end there. Later theoretical tinkering revealed a potential loophole. By reshaping the warp bubble itself, oscillating its geometry, or making it into a thinner, more dynamic ring, some physicists have suggested the energy requirement could be lowered dramatically, perhaps even to something comparable to the mass of a small spacecraft. This single shift transforms the Alcubierre drive from a physical impossibility into a distant, but conceivable, engineering challenge. It stands as the ultimate expression of our desire to explore, proving that the laws of physics might still hold secrets that allow us to traverse the galaxy. But before we can dream of commanding the fabric of space-time, we must first prove we can reliably cross our own cosmic backyard, mastering the high-speed travel that will serve as our essential training ground for the stars. An engine that can think for itself, shifting its power like a car changing gears, has long been the dream of mission planners. This is the core promise of the VASIMR engine, or the Variable Specific Impulse Magnetoplasma rocket. Unlike a traditional engine with one fixed setting, VASIMR uses a sophisticated two-stage process to give pilots a choice. First, a neutral gas like argon is injected into a chamber, where powerful radio waves, similar to those in a microwave oven, blast the atoms, stripping away their electrons and creating a super hot soup of charged particles called a plasma. This glowing fourth state of matter is then funneled through a second stage, where even more energy is added and finally guided out by a magnetic nozzle to produce thrust. The true genius lies in its variability. Need to get a cargo shipment to Mars quickly, run the engine in high thrust mode, sacrificing some fuel efficiency for a faster transit. Planning a long-duration robotic mission to the outer planets, switch to high-efficiency mode, conserving precious propellant for the multi-year journey. This adaptability makes it an ideal workhorse for a bustling solar system, capable of rolls from orbital tugboat to interplanetary freighter. Championed for decades by former astronaut Franklin Chang Diaz, VASIMR is a modern evolution of those foundational electric propulsion concepts, yet it has never been the primary engine on a major NASA mission. It consistently loses out to the brute force simplicity of chemical rockets, which are well understood and reliable for short bursts. The reason is simple: VASIMR is incredibly power-hungry. To achieve its impressive thrust levels, it requires a massive and steady supply of electricity, far beyond what today's standard solar panels can provide. The key to unlocking its full potential, therefore, does not lie within the engine itself, but in the system that powers it. For VASIMR to truly revolutionize our travel to Mars and beyond, it needs to be paired with a powerhouse that can meet its voracious appetite, a development that points directly toward the next great leap in space-based energy. A miniature nuclear reactor, no larger than a garbage can, could one day power an entire city on Mars. This is the Kilopow reactor, a tested and proven system that transforms a decades-old need into a tangible piece of hardware. While solar panels are effective in the inner solar system, they become useless during the 2-week-long lunar night or on the dust-choked surface of the red planet. Kilopow offers a solution that is both constant and rugged. Its design is a masterpiece of simplicity and safety. At its heart sits a solid core of enriched uranium, a design that avoids the complex pumps and control rods of traditional reactors. The heat from fission is carried away by passive sodium heat pipes, a system with no moving parts that relies on the fundamental laws of thermodynamics to transfer immense thermal energy. This heat is then converted into electricity by a bank of efficient Stirling engines. The entire system is self-regulating. If it gets too hot, the nuclear reaction naturally slows down. This inherent safety means it could be launched from Earth in a dormant state, only becoming operational once it is safely deployed on another world. A single 10-kilowatt unit could provide all the electricity needed for a robust outpost, running life support, manufacturing breathable air, and purifying water. With a cluster of them, you could even power the machinery to crack lunar ice into hydrogen and oxygen, manufacturing rocket fuel for the journey home. Kilopow is the bedrock upon which a true off-world civilization can be built, providing the unwavering energy that turns survival into sustainability. But once we have a steady and powerful supply of electricity on the Moon, the next logical step is to ask what we can build with the very ground beneath our feet. This quiet revolution is already underway, humming inside a small box aboard the International Space Station. A specialized 3D printer, designed for the peculiarities of zero gravity, has successfully created tools and spare parts from plastic filament, proving that manufacturing in the void is not only possible but practical. But this is just the first, tentative step. The true potential lies in scaling this process into full-blown orbital factories. Imagine facilities where robotic arms guide laser nozzles, sintering fine metal powders into complex engine components or structural beams, all while floating in the high vacuum of space. The raw materials for this industry would not be intricate, pre-assembled machines launched at astronomical cost, but simple blocks of polymer, rolls of composite filament, and canisters of metal powder. These are dense, uniform, and far cheaper to send into orbit, fundamentally altering the economics of building anything beyond our atmosphere. Such a capability would transform our approach to exploration. A mission to Mars would no longer need to carry every conceivable spare part for a 7-year journey. Instead, the crew could simply transmit a digital file and print a replacement wrench, a custom medical device, or a critical plumbing component on demand. Even more profound is the ability to create structures that are simply impossible to launch. We could print vast antenna dishes for deep space communication, gossamer thin solar arrays the size of football fields, or the intricate framework for a generation ship, all designed for the environment of space without ever having to survive the violent shaking of a rocket launch. The hurdles, however, are significant. How do you ensure a perfect print when molten material behaves unpredictably without gravity to anchor it? How do you manage the fine, potentially hazardous metal dust in a closed environment? And how do you establish a reliable, cost-effective supply chain to keep these cosmic workshops stocked? Solving these problems is the essential bridge from merely visiting space to truly industrializing it. Once we can reliably build with materials we bring from Earth, the next logical, and even more transformative, step is to learn how to build with what we find already waiting for us out there. A robotic factory on Mars needs no supply ships from Earth to manufacture its most vital product, rocket fuel. It simply harvests the very air of the red planet. This is not science fiction, but the practical reality of in situ resource utilization, the art of living off the cosmic land. The principle is the ultimate form of sustainability. Instead of hauling every ounce of water, air, and fuel on a multi-year journey at astronomical cost, we send smart, automated machinery that can extract what we need from the soil and atmosphere of other worlds. On the Moon, that means baking the powdery regolith to release vast quantities of oxygen, a process that could fill the life support tanks of a lunar base. On Mars, the technology becomes even more powerful. The Perseverance rover carries a toaster-sized instrument called MOXIE, which has already proven the concept. It sucks in the thin Martian air, which is 95% carbon dioxide, and electrochemically splits each molecule into pure carbon monoxide and a vital breath of oxygen. Scaling this process up is the next logical step. Imagine a larger plant that uses solar power to not only create oxygen for astronauts to breathe, but also to combine it with hydrogen, harvested from Martian water ice, to create liquid rocket fuel right there on the surface. This single capability transforms the entire economics of exploration. A mission to Mars no longer needs to carry the immense weight of fuel for the return journey. The spacecraft arrives light and the crew departs heavy, refueled by the resources of their destination. Mars stops being a one-way cliff and becomes a roundabout, a gas station on the interplanetary highway. This is the grand promise of ISRO, turning dead worlds into supply depots and enabling a future where we are not just visitors, but true inhabitants of the solar system. And this profound shift in logistics, from carrying everything to making what you need where you are, forces us to reconsider the very paths our ships take through the void. A cosmic bus route already exists in the silent mathematics of gravity. This is the Aldrin Cycler, a concept for a permanent interplanetary commute. Instead of building a new ship for every trip to Mars, we would construct a large, comfortable habitat once and set it on a precise, repeating orbit between the two worlds. Think of it as a celestial ferry on an endless loop, a vessel that requires only occasional nudges to maintain its schedule as it swings past Earth and Mars at predictable intervals year after year. When the cycler approaches, smaller, specialized taxicraft would launch from the planet's surface, carrying passengers and cargo to rendezvous and dock with the larger ship. The crew would then transfer into a well-appointed, heavily shielded home for the multi-month journey, a vessel designed from the start for long-term comfort and safety before taking another taxi down to the surface of their destination. The beauty of this system is its reusability and efficiency. The most massive and complex component, the living quarters, is used over and over, drastically cutting the cost and complexity of each individual mission. It transforms the epic challenge of a Mars voyage into a manageable, regular logistics operation. The initial setup, of course, is a monumental task. It demands incredibly precise orbital calculations and the construction of a sizable, permanent station in a transfer orbit. Yet, once established, this cycler becomes a foundational piece of a true interplanetary infrastructure, the backbone of a bustling solar system economy. But to build such enduring structures capable of withstanding decades of cosmic radiation and micrometeoroid impacts, we require materials far superior to anything we use today. This pressing need for revolutionary alloys and composites pulls another forgotten concept from the archives, one that proposed creating them in the one place where perfection is easier to achieve. That ribbon woven from carbon nanotubes would be the ultimate bridge to the stars, a permanent highway stretching 62,000 miles into the sky. The space elevator is a concept of breathtaking elegance, a structure that replaces the violent, explosive power of rocketry with the silent, steady climb of an electric railway car. Imagine a cable anchored at a floating platform on the equator, extending far beyond the height of geostationary orbit, where satellites appear to hang motionless in the sky. At that distant end, a massive counterweight, perhaps a captured asteroid, would pull the entire structure taut, using the centrifugal force of Earth's own rotation to keep the ribbon standing upright against gravity's constant pull. Electric climbers, drawing power from lasers on the ground, would glide up and down this tether, carrying cargo and eventually people into orbit for a tiny fraction of today's cost. This is not just an incremental improvement, it is a complete paradigm shift. The primary obstacle has never been the physics, but the material. We need a cable with a tensile strength beyond any metal, a material that can withstand the immense stress of its own colossal weight. Carbon nanotubes, with their theoretical strength 100 times greater than steel, are the only candidate. Yet, the challenge of weaving these microscopic tubes into a flawless, continuous ribbon thousands of miles long remains one of the most daunting in all of engineering. We can create short strands, but achieving the required purity and length on an industrial scale is a problem we have not yet solved. If we can, the entire solar system opens up. The space elevator would make every other concept in this video infinitely more feasible, providing the cheap, reliable access to orbit needed to build the Aldrin cyclers, the orbital factories, and the solar power satellites that will define our future. With such a gateway in place, we could deploy scientific instruments of a scale that is currently unimaginable, missions designed not just to visit other worlds, but to fundamentally understand the cosmos. Our own sun could become the most powerful telescope ever conceived, a cosmic lens of unimaginable clarity. This is the principle of the solar gravitational lens, a mission that would use the sun's immense gravity not as a force to overcome, but as a tool for supreme discovery. Einstein's theory of general relativity tells us that massive objects warp the fabric of space-time, bending the path of light that travels near them. Our Sun does this constantly, creating a natural, though usually imperceptible, lensing effect. The genius of this concept is to position a spacecraft at the precise point where this bent light comes into a perfect focus. That focal line begins an astonishing 550 astronomical units from the Sun, a distance that makes Pluto's orbit seem like a local neighborhood. At this unimaginable remove, the starlight from a single exoplanet, warped by the Sun's gravity, would form a brilliant ring around our star, an Einstein ring containing all the light from that distant world. A telescope positioned here would not see a faint, twinkling dot. It could, in theory, resolve the surface of that planet with a magnification of 100 billion. We are not talking about detecting atmospheric gases. We are talking about mapping continents, observing cloud movements, and discerning the patterns of oceans and deserts on a world orbiting another star. The mission, championed by physicist Claudio Maccone, would be the ultimate astronomical observatory, a single instrument capable of answering the oldest question of all: are we alone? The challenge is not the theory, but the sheer, staggering distance. A journey to the solar gravitational lens is a voyage that would take many decades with current propulsion. It demands an engine of both immense power and incredible endurance, something like a nuclear electric or even a fusion drive, capable of a sustained push for years on end. But to operate so far from the Sun's fading light, where solar power is a useless memory, such a spacecraft would need its own brilliant, long-lasting star for power. This brings us back to a fundamental source, but one reimagined for the darkest, coldest reaches of space. Fusion's greatest challenge has always been containment, the struggle to bottle a star. But today, we are building smarter bottles. The direct fusion drive represents a radical evolution of the Daedalus concept, trading its colossal scale for a compact, elegant design. This engine would use anotronic fusion, a reaction between deuterium and helium-3 that releases its energy as charged particles instead of destructive neutrons. This is a critical distinction. It means the raw power of the reaction can be channeled directly by magnetic fields, creating thrust without the need for a heat exchanger or a separate turbine. The super-hot plasma itself becomes the propellant, shot out the back at a significant fraction of light speed. The result is the once mythical combination of high thrust and high efficiency, an engine that can accelerate continuously for months, cutting the trip time to Saturn from years to mere months. And because the process generates vast amounts of electricity as a byproduct, the same compact reactor that pushes the ship also powers all its systems, from life support to scientific instruments, for the entire duration of a multi-decade mission. This leap is only possible now because of two key innovations. The first is high-temperature superconductors. These advanced materials can carry immense electrical currents with zero resistance, generating the powerfully compact magnetic fields needed to squeeze and control the fusion plasma without requiring a massive, power-hungry cooling system. The second, perhaps even more crucial, is artificial intelligence. Fusion plasma is notoriously unstable, a writhing, complex structure that can collapse in microseconds. No human operator could possibly react fast enough, but an AI control system can, constantly monitoring millions of data points and making micro-adjustments to the magnetic fields thousands of times per second to keep the miniature star perfectly stable and burning bright. Private companies like Princeton Satellite Systems are actively developing these systems, leveraging computing power and material science that simply did not exist when these ideas were first dreamed up. This revival proves that a forgotten concept is not a dead one, it is merely waiting for its time, and as our engines grow more capable of carrying us farther and faster, we must also ensure they are carrying a living world within them, a self-sustaining bubble of earthly life for the long journey ahead. A spacecraft that breathes, drinks, and eats for itself represents the final frontier of life support. This is the vision of a closed ecological life support system, a self-contained biosphere where every molecule of air and water is endlessly renewed through a delicate dance of biology and engineering. Think of it as a miniature Earth in a can, a world where plants convert the carbon dioxide we exhale back into fresh oxygen, where specialized microbes break down our waste into nutrients, and where every drop of perspiration or condensation is captured, purified, and returned to the system as clean drinking water. We have already taken the first tentative steps toward this future. The International Space Station recycles about 90% of its water, a remarkable feat of engineering. And the ambitious, if troubled, Biosphere 2 experiment here on Earth showed us both the profound potential and the immense difficulty of creating a stable, sealed environment. The next leap involves integrating advanced hydroponic farms that grow vegetables without soil under glowing LED suns, and algae bioreactors where green, single-celled organisms work tirelessly as tiny chemical factories, scrubbing the air and providing a rich source of protein. The technical hurdles are immense, requiring a system robust enough to withstand a sudden crop failure or a microbial imbalance without endangering the crew. Yet the biological challenge is matched by a psychological one. Living inside a machine that is also a living world, where your every breath is part of a cycle you cannot afford to break, imposes a unique mental burden. Perfecting this closed loop is the ultimate key to cutting the umbilical cord to Earth. It transforms a spaceship from a vulnerable lifeboat carrying finite supplies into a resilient ark, capable of sustaining its inhabitants indefinitely on a voyage to another world. This self-sufficiency is the grand, unifying thread that connects every forgotten concept, from the engines that push us to the factories that build us. It is the final, necessary step to ensure that when we leave, we are not just visiting the cosmos, but moving in for good. That same principle of reusability found in the Aldrin cycler applies not just to entire ships, but to their very building blocks. A spacecraft does not have to be a single, fragile, custom-built machine. The modular architecture vision reimagines space exploration as a cosmic construction set, where every mission is assembled from a library of standardized, interchangeable parts. Think of a propulsion bus, a self-contained unit with its own fuel tanks and engines, designed to dock with a generic command module, a power module, a sprawling wing of solar arrays, or a compact nuclear reactor could plug into any vessel needing electricity. Habitation rings, science laboratories, and cargo pods would all share a common docking interface, allowing them to be mixed and matched like the most sophisticated Lego set ever conceived. A robotic survey of Venus could be configured 1 year using a high-thrust chemical module for a quick journey. The next mission, a long-duration tour of the asteroid belt, could use the exact same command pod and lab, but swap in a high-efficiency VASIMR engine for the multi-year cruise. This philosophy shatters the old paradigm of designing a new billion-dollar spacecraft from the ground up for every single objective. Instead of being disposable, the expensive components are reused again and again, with only the specialized payloads needing to change. We see a primitive, first-generation version of this in the International Space Station, a patchwork of modules from different nations assembled over decades. But a truly universal, deep space architecture was always just out of reach, a casualty of the same budget pressures that shelved the Space Tug. Now, as private companies plan their own commercial stations and new vehicles designed for orbital docking, the pieces are finally falling into place for this forgotten dream to become our operational reality. This modular future gives us the ultimate flexibility to adapt, to repair, and to evolve our presence in space, building not just single missions, but a permanent, growing infrastructure among the stars. A clear pattern emerges from these forgotten blueprints, a story not of failure but of timing. These revolutionary engines and cosmic habitats were not defeated by physics, but by the earthly realities of their era. They were victims of shrinking budgets, shifting political priorities, and a technology base that simply was not ready. The fierce, singular focus on winning the moon race left countless deep space concepts stranded on the drawing board. When the Cold War tension that fueled so much aerospace research began to fade, the perceived urgency for these ambitious systems faded with it. The grand visions of nuclear starships and orbital colonies were quietly shelved, not because they were impossible, but because the world momentarily turned its gaze elsewhere. Yet the very problems these concepts were designed to solve have not gone away. The challenge of surviving cosmic radiation, the immense cost of lifting material from Earth, the sheer duration of a journey to Mars, these are the very obstacles we face today. And now the landscape has fundamentally shifted. We are living through a perfect storm for their revival. The rise of a vibrant commercial space industry has shattered old cost models and introduced a new culture of speed and innovation. Breakthroughs in artificial intelligence offer the precise control needed to stabilize a fusion plasma or manage a complex closed-loop life support system. New materials like high-temperature superconductors and graphene provide the physical tools to build magnetic shields and solar sails that were once pure fantasy. A renewed global race to the moon and a persistent ambition for Mars have created a clear and present need for the solutions these old blueprints contain. These forgotten concepts are far more than historical curiosities. They are a pre-made roadmap, a treasure trove of well-studied, mathematically sound answers to the questions we are only now learning how to ask. They stand as a powerful reminder that progress is not always a straight line. Sometimes the most direct path to our future lies in rediscovering the brilliant ideas we left behind. From the atomic fire of Project Orion to the silent glide of a solar sail, we have uncovered a legacy of breathtaking ambition lying dormant in history. These forgotten concepts are far more than old blueprints gathering dust. They are a powerful testament to human ingenuity and our persistent belief in a future among the stars. Each one, in its own brilliant way, addresses a critical piece of the interplanetary puzzle. We need propulsion to cross the vast distances, power to fuel our engines and our homes, protection from the deadly void, and a plan for permanence to build a civilization beyond our world. As we stand on the cusp of a new space age, with rockets re-landing and new stations being planned, these rediscovered ideas offer us an incredible head start. They provide a pre-tested foundation, a treasure trove of solved problems, upon which we can finally build our cosmic future. The greatest revolution in interplanetary travel might not be a brand new discovery, but the powerful rediscovery of our own potential, waiting patiently for its time to come. So we are left with one final, reflective question. What forgotten idea from today's journey will light the spark for the generation of tomorrow? Which of these cosmic dreams will you help bring to life? Share your thoughts in the comments below and subscribe for more journeys into the future waiting to be built.